let's have a look at how we would write an electron configuration using our more advanced structure of the atom. In the last video I showed you that there are different energy levels and different orbitals and the number of different orbitals present in an atom. And what I've got here is a graph where we have energy as our y-axis. We have the lowest energy at the bottom and the highest energy at the top. Now, you hopefully will remember that the principal quantum number is equal to an energy level or an electron shell. So the lowest energy of that is 1. So our energy level down here is the lowest, so this will be where the first shell is, and as we go up we will get more and more electron shells with a higher principal quantum number. The second thing to remember is that the different types of orbital in the first energy level, I'm just going to put 1 there, this is the first energy level, we only have one type of orbital, and that is an s orbital, and there is only one of them. In the second energy level we have an s, and we also have p orbitals, and so we have 2 types of orbital. We have 3 p orbitals like that, and important to note here that the p orbitals are at a very slightly higher energy level than the s orbitals. Going up to the third one, we have s, p, and all the way up here, d. And that pattern will continue. Now I've only included the first 2 orbitals of the fourth energy level, the fourth energy shell, electron shell, in my diagram, because you generally aren't expected to go any further in terms of writing electron configurations at A level. But if I put 4s here, and if I put 4p here, the 3D channel is all the way up here. It's actually sitting somewhere in between 4s and 4p. Okay, so it's higher than the 3p, and actually even slightly higher than the 4s in terms of its energy, but below the 4p. Now this is an empty atom. This is where we would calculate where these electron orbitals would be if we just had an empty atom. What's important is that as soon as we start putting electrons in, we actually affect the energy levels slightly, and so these do kind of change depending on whether we've put electrons in or not. Most of that change is irrelevant at A level, but there is one very special case where it's very important. So when we look at an atom of hydrogen, it has 1 electron, and the electron goes in the lowest shell. Now at GCC we said that was the inner shell, and here it is the one with the lowest energy value. Now we start with the lowest energy. That's actually a principle known as the Aufbau principle, which means that we are filling from the lowest energy up towards the highest energy, and so you can see that we have an order of energy with respect to each orbital. So we can see that we'll fill them up in this sort of order. So for hydrogen, we would have an electron configuration of 1s and then 1. The 1 meaning the principal quantum number, the s meaning the orbital, and then the superscript 1 meaning how many electrons are in that orbital. The second principle that we have is something called the Pauli Exclusion principle, and that means basically that if you have 2 electrons in this s shell, they will have what we call opposite spins. Now spin is just a property of an electron. It comes from a quantum number, but all we need to know at this stage is that we have 2 electrons in the same orbital. They must have opposite spins. So for helium, which has 2 electrons, our electron configuration would, instead of being 1s there, with just one electron in, it would have a second electron in that shell of an opposite spin. For helium, when we add our second electron, it has an opposite spin. It still goes in that first orbital, and now we have an electron configuration of 1s2, because it's quantum number 1, s orbital, 2 electrons. Now at this point we've got to the maximum number of electrons we can fit in an s orbital, which is 2. And so when we come on to the next one, which is lithium, we're going to have our first electron being in this next energy level up, which is the 2s orbital. And that gives our electron configuration now as 1s2, we've got this one filled as we had before, 2s1. So the first shell has an s orbital with 2 electrons in, the second shell has an s orbital with 1 electron, and everything else is empty. We can continue down this route. We so for beryllium, we would fill one in here, and then for boron, we would fill the next one in here. And so we would have, for beryllium, it would be 1s2, 2s2, and then for boron, it would be 1s2, 2s2, and then we would say 2p1. So we're just listing the orbitals in order according to how many electrons there are. Now at this point we have to introduce a new principle, and these are called Hund's rules. And Hund's rules are a collection of rules which basically, for us at A level, boil down to this: if we have multiple orbitals of the same energy available, then it's more energetically favourable to have the electrons in different orbitals, otherwise you get repulsion between them. And repulsion between them raises the energy. So when we get to carbon, we now put our next electron in the next p orbital, not pairing them up at this stage. And when we get to nitrogen, that one will go in here. We will have those all in separate orbitals. Now for nitrogen, we would have the electron configuration 1s2, 2s2, 2p3. At this point we get to oxygen, and with oxygen we've now got 3 p orbitals at the same energy level, but 4 electrons to fit into them, and so we would have to start pairing them up. It's still more energetically favourable to pair them up than it is to go to the next energy level. So oxygen we'd fill like that, and then when we come to fluorine, we put that there. Then when we come to neon, we would pair them up like that, which means that neon's electron configuration would be 1s2, 2s2, 2p6. So when we come to the third shell, we use the same rules as we did before. Sodium starts with 1 electron in the 3s orbital, and then when we come across to magnesium, we end up with a second electron in the s orbital as well. And then when we get to the p orbitals, we fill them the same as we did before. So aluminium would be 1 in there. Silicon would have 1 in there and 1 in there. And then we would have for phosphorus, all 3 separately. All of them are in this 3p subshell, but each of those are in a different orbital. And we can continue in the same way as with the 2p. We would go from there, we would go sulfur, would have that one, and then chlorine would be like that, and then argon would be like that, and we can continue filling up this way. So potassium, calcium. we now get to the same stage again where the rules change slightly, and what we now see is that the reason the transition elements are so difficult to work out what's going on with that circular model is that actually these electrons here are actually part of this energy level here. But they're so high energy that they actually overlap. So we've got a bit of overlap between these two energy levels here. And what I want you to understand is that when we have been filling these in, we have been comparing one atom to another. We don't have an empty nucleus and start throwing electrons at it to fill it up. Okay, we are comparing one with another, and the electron configuration is different. So when I start to fill this 3D shell, if I had scandium 3+, it would have everything up to the 3p subshell full, and then if I added 2 electrons to that, it would go. They would both go in the 4s. And subshell. The act of putting the last electron in actually changes this energy level. It actually draws it very slightly closer to the nucleus, if you like, or slightly lowers the energy. And that means that the 4s shell is now higher than the 3D shell. So the electron configuration for scandium is 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1, and then 4s2. And the important thing I find about writing it this way, you can write it with these two the other way around, as if you were filling it in order of the lowest energy level when they were empty. But I find writing it this way is better because it reminds you that when you make ions from this electron configuration, you are actually taking out the highest energy level first, which isn't the 3D. The 3D has now dropped below the 4s. They're so similar in energy that it's only a very small change, but nonetheless, it's dropped below the 4s, and now this is the highest energy level. So when we start to take electrons out, we start with the 4s and not with the 3D. So when we're working out titanium's electron configuration, we need to imagine this as being up here and empty, and we fill up all of this, and then we go 1, 2 electrons in the 3D. They're in separate orbitals because these are all at the same energy level, and then we drop this down below the 4s. So when we're filling in the next one, if we're filling in vanadium, again we fill it up like that, and then we drop it down like that. So we get to manganese, which has 5 electrons in its D shell. And we, and then again that would drop down like that, so the 4s is removed first. But when we get to the next one, we get to iron, we've now got 6, so we start to pair up like that. Okay, so iron, and then cobalt, nickel, etc. So we look at nickel's electron configuration. We have 1s2, 2s2, 2p6, 3s2, 3p6, 3, almost fell for it, D, 2, 4, 6, 7, 8, 4s2. When we get to the end of the D shell, we just carry on as normal. We go up to the 4p. So gallium would be like this, and then we would go to germanium, then we go to arsenic, and we would fill up the electrons exactly the same as we did for the other p shells. So our 3 principles are low energy first, high energy afterwards. Electrons in the same orbital have opposite spins, as shown by up and down arrows. And if you have multiple orbitals of the same energy level, you have to fill them all with 1 electron before you start pairing them up.